Good day. For those of you who do not know us, we're the instructional staff for EC 150, Professors Hiran Patel and Werner Dietl, and Douglas Harder. In this topic, we're going to discuss and introduce binary and hexadecimal numbers. So in this lesson, we're going to review counting. We will then consider what would have happened had we had only 8 fingers instead of 10. We will then introduce binary numbers, and we will look at the addition of binary numbers. We will then introduce hexadecimal numbers and see how hexadecimal numbers can be used to represent binary numbers. Now, in our counting system, we have 10 different unique digits, and from these digits, we produce numbers. This is not necessarily the way you must do this. In ancient Babylonia, they had a counting system that had essentially 60 different digits. Also, our numbering system is positional. That means the significance of a digit depends on where it appears in a number. Again, this is not always the case. In ancient Hebrew, every letter represents a number. So here we see the name David. D represented 4, Vav represented 6, and so here we have 4 plus 6 plus 4. So this is one representation of the number 14. However, in our system, the significance of a digit depends on where it appears in a number. So for example, if I give you the number 1942, the 2 represents 2 times 10 to the 0, or 2 times 1, which is 2. 4 represents 4 times 10 to the 1, or 40. The 9 represents 900, and the 1 represents 1000. The number 1942 represents the total of these 4 separate numbers. Another thing to note is, remember that the digit 9 represents as many objects as you see there, and consequently, the next larger number represents 1 additional object, or what we would consider 10 objects. Now, base 10 is great for human beings because we have 10 fingers. Suppose humans had only 8 fingers. In this case, we probably would have only come up with 8 digits. Indeed, if we have only 8 digits, that means we have only 8 fingers. Oh well, carrying on. Thus, our numbering system would look like the following. After 7, there's no more digits, so now we have to go to 10. So consequently, 10 would represent one more thing than 7. 7 represents 7 objects. 10 in base 8 would represent 8 objects. Also, if we were to do addition in base 8, then 2 plus 3 is 5. All right, not a problem. 3 plus 7. Well, looking at this chart, 7 next is 10, then 11, then 12. So it seems that 3 plus 7 is 12. So we'll put the 2 there and we'll carry the 1. 1 plus 5 is 6. And so therefore we'll just put 6 down there. 6 plus 3 is 1. So we'll put the 1 there and carry the 1. 1 plus 7 plus 4 is 14. And so then we would put down the 4 there and carry the 1. 1 plus 5 is 13. We'll write down the 3, carry the 1. 1 plus 3 plus 1 is 5. So we'll put the 5 there. 4 plus 6 is 12. We'll put the 2 down there, carry the 1, and of course 1 plus 0 is 1, and so we'll place the 1 there. So we could actually do counting and addition in base 8. You will not have to do this in this course. What I was doing here was simply showing you how counting would have appeared had we chosen a different number of digits, say 8. So in this case, 1 0 in base 8 would actually represent 8 things. 1 1 in base 8 would represent 9 things, and 1 4 in base 8 would represent what we would consider to be a dozen. Okay. Again, it's beyond the scope of this course, but to convert a base 8 number, let's say that this 4173 is a base 8 number. If we wanted to convert this into a base 10 number, this would be 3 times 8 to the 0, which is 3, plus 7 times 8 to the 1, which is 56 in decimal, 1 times 8 squared, which is 64, and 4 times 8 cubed, which happens to be 2048. Thus, 4173 in base 8 is 2171 in decimal. In a computer, however, a number must be stored as a voltage, and you're going to learn more about this on your courses in digital circuits and digital computers. Having 10 different voltages, each separate voltage representing a different decimal digit, is actually very difficult to design and maintain. Some of the earliest computers, yes, did in fact use a base 10 system, and this was back in the 1940s. However, this was found to be unmaintainable and inefficient. Instead, it is easiest to have only 2 voltages. 0 is represented by 0 volts, and 1 is represented by 5 volts. Consequently, we have only 2 base 2 digits, or only 2 binary digits, 0 and 1. It's as if we were counting with our arms rather than with our fingers. We will call 0 and 1 to be bits, and that comes from an abbreviation of the word binary digits. So this means we only have 2 bits now, 0 and 1. So thus, after we have counted one object, the next number is represented by 1 0. So 1 plus 1 is equal to 10, or 1 0. In binary, 1 0 plus 1 is equal to 1 1. And the next number after 1 1 is 1 0 0. I'm trying not to use the word 100 because 100 is the word we use to represent 10 groups of 10 objects. Thus, the binary number in the first column represents the number of objects in the second or third columns. So, for example, the binary number 101 represents 5 objects, or the number of objects we see here. Similarly, the binary number 1011 would therefore represent 11 objects, or the number of objects we see on the right-hand side. So here are some very useful binary numbers to remember. 1, of course, represents 1 or 2 to the 0. 1 0 represents 2 to the 1 or 2. 1 0 0 represents 2 to the 2 or 4. 1 with 3 zeros represents 2 to the 3 or 8. 1 with 4 zeros represents 2 to the 4 or 16. 1 with 7 zeros represents 2 to the 7 or 128. And very importantly, notice that 1 with 10 zeros represents 2 to the 10. But 2 to the 10 is actually very close to 1000. It's actually 1024, and this is a number you'll want to remember, but it's very useful that this number is very close to 1000. As you may guess, 1 with 20 zeros is therefore very close to 1000 squared, or 1 million. Now, adding numbers in base 10 is something that you've learned since elementary school. So here we see the sum of 6 decimal numbers. How did we get this? Well, we added the least significant column to get the value 32. 32, we write down the ones digit, which is 2, and we carried the 3. We then added the second column from the right to get 18. We wrote down the 8 and we carried a 1. We summed up those 4 numbers and we got 4, so we just wrote down the 4. And of course, 1 by itself is equal to 1. If in base 10 you're adding powers of 10, this gets even easier. 10 plus 100 plus 10,000 is just that number we saw there on the right. We just we didn't even have to do any carries or anything significant. We just wrote down the appropriate ones. Well, fortunately, adding powers of 2 in base 2 is also quite easy. It's as easy as adding powers of 10 in base 10. So here we see 6 binary numbers that represent the decimal numbers on the right. How do we add these up? Well, 0 plus 0 plus 0 is, well, just 0. 1 plus a whole bunch of zeros is still 1. Adding a whole bunch of zeros still adds to 0. Adding 1 to a bunch of zeros is 1. Here we have a number of zeros. Again, adding a number of zeros. 1 plus 3 zeros is 1. 1 plus 2 zeros is 1. 1 plus a 0 is 1. 0 by itself is 0. And 1 by itself is 1. That was really easy. We didn't even have to do any carries. So the number on the right, 10111 001010, represents the number of objects that we would normally call 1,482 objects. Nice. Now, in every base 10 number, a digit is associated with a power of 10. So in this number, 123,456,789, we will say that the 9, which is 9 times 10 to the 0, is going to be in the 0th position because it's associated with 10 to the 0. The digit 8 in this number represents 8 times 10 to the 1, so we'll say that the 8 is in the 1st position. And the 1 represents 1 times 10 to the 8, and so we will say that the 1 is in the 8th position. So our position numbering will start at 0 on the right-hand side. Thus, to figure out what a binary number represents in decimal, we have the following. Here's an example. The 1 is in the 0th location, so the first one there represents 2 to the 0, or 1. The next one is in the 2nd position, so we will say that this represents 2 to the 2 or 4. This one here is in the third position, so it represents 2 to the 3 or 8. The one in the fourth position represents 16. The number in the seventh position represents 2 to the 7 or 128. And finally, the last one there is in the 11th position, so it represents 2 to the 11 or 2048. Thus, this binary number represents 1 plus 4 plus 8 plus 16 plus 128 plus 2084 or 2205. Now, in adding two binary numbers, the process is the same as adding two decimal numbers. However, instead of having to know how to add 4 and 7 and 3 and 8 and 2 and 9, we only have to know how to add 1 and 0. So we only really have to remember that 1 plus 1 is equal to 1, 0, and 1 plus 1 plus 1 is equal to 1, 1. All right, easy enough. So if we were to add these two binary numbers, we start at the least significant bit. 1 plus 0 is 1. 0 plus 0 is 0. 1 plus 1 is 1, 0. So we'll write down the 0 and carry the 1. 1 plus 1 plus 0 is still 1, 0. So we write down the 0 and carry the 1. 1 plus 0 plus 0 is 1. 1 plus 1 is again 1, 0. So we write down the 0 and carry the 1. 1 plus 1 plus 1 is 1, 1. We write down the least significant bit 1 and we carry the 1. 1 plus 0 plus 1 is 1, 0. We write down the 0, carry the 1. 1 plus 0 plus 0 is 1. 0 plus 0 is 0. 1 plus 1 is 1, 0. We write down the 0, carry the 1. 1 plus 1 is 1, 0. We write down the 0, carry the 1. And 1 plus 0 is just 1. And we're done. Humorously enough, we can even check our answer. Notice that in decimal, the first number represents 1 plus 2 to the 2 plus 2 to the 3 plus 32 plus 64 plus 1024 plus 2048. If we add all these numbers up, the first binary number represents 3181. The second number, if we look at each of the 1 bits, we see that the second number represents 4 plus 32 plus 64 plus 128 plus 1024. Adding all of these together gives us 1252. If we look at the answer is 1 plus 16 plus 64 plus 256 plus 4096. If we add all of these together, we get the number 4,433. And as you can see, 4,433 is equal to 3,181 plus 1,252. Now this begs the question, if we see the number 100, does this represent what we consider to be 100, or does it represent 2 to the 2, which is 4? We will normally prefix binary numbers with the 2 characters 0b, and we'll see why later. We will also normally use the monospace typeface consolus. Thus, the first number there, 100011010, actually represents 100,011,010. However, those same ones and zeros prefixed with a 0b and written in the consolis typeface will represent the binary number that represents 1970 or 1970. On occasion, we may gray out the 0 and B just so that you can focus on the binary number, with the gray 0B just giving you a hint that yes, this is a binary number. Now, just like adding with decimal numbers, you can do the same with binary numbers. Here are some examples that you can try yourself at home. Try adding both of these binary numbers on the right and see whether or not you get the correct answer. Now, there are only 10 types of people in the world. Those who understand binary and those who do not. Now, it seems that it takes many more bits to represent a number in binary than it takes for the number of digits necessary to represent that same number in decimal. It's actually not that bad. It only takes approximately log base 2 of 10, or 3.3 times as many bits as it requires digits. So for example, 8,357 requires 4 decimal digits. It would therefore require approximately 13.2 bits. Well, in fact, it actually requires 14 bits, but close enough. The computer doesn't care. It's easier to work with binary, but for humans, it's very frustrating to deal with long strings of ones and zeros. And so we're going to look at a more compact representation of binary numbers. Suppose instead we had 16 fingers or 16 digits. In that case, we might count in base 16 and not base 10. All right, so in that case, we need 16 unique digits. The easiest, of course, with the standard keyboard is to just start using something else, and the easiest to use is the letters of the alphabet. So here we have 16 unique digits, and 9 represents 9, A represents what we consider to be 10 things, B represents what we consider to be 11 things, C is a dozen, D is 13, and F is 15. Consequently, 10 represents 16 objects. Just like 10 in decimal represents 10 objects, 10 in binary represents 2 objects. So 10 in base 16 or hexadecimal represents 16 digits, 16 objects. Now this begs the question again. Is 5923 actually equal to 5,923, or is it something else in base 16? Well, again, we are going to prefix any hexadecimal number with 0x, the x from the hexadecimal, and we will again also use the monospace typeface consolis. Thus, if you see 5923 in Times New Roman, that's a decimal number. However, if you see 0x5923, that's a hexadecimal number, and it happens to represent the decimal number 22,819. But you don't have to worry about how to get that. To start off again, we may occasionally gray out the 0x if we want to emphasize the hexadecimal number. Now, it seems that if we are dealing with base 16 instead of base 10, it should require fewer hexadecimal digits to represent a number in hex than it does to represent that same number in decimal. And again, hexadecimal is sometimes abbreviated as simply the word hex. However, it's not that much better. It's only slightly better. So normally it takes log base 16 of 10, or 0.83 times as many hexadecimal digits to represent the same decimal number. So for example, the decimal number 8,357 requires 4 decimal digits. It would require therefore approximately 3.32 hexadecimal digits. It actually still requires 4, but close enough. Now, why are we introducing hexadecimal at the exact same time that we're introducing binary? Well, basically hexadecimal is just an easy way to store a binary number. Now, on the left-hand column, we see the digits from 0, or the numbers from 0 to 15. In the second column, we see those 16 numbers in binary, and in the third column, we see the corresponding hexadecimal numbers. You'll notice that the first 16 numbers, going from 0 to 15, are represented by only a single hexadecimal digit, whereas for binary, it requires up to 4. Now, let's just pad each of the binary numbers so that each binary number has 4 bits in it. You can now see that every possible combination of 4 ones and zeros is represented by a unique hexadecimal number. So, for example, 1000 can be represented by 8. 1101 can be represented by D, and 4 ones can be represented by F. So the only thing we're going to do is use hexadecimal numbers to represent a binary number. To convert a binary number into hexadecimal, such as this one, all we do is we split the binary number into groups of 4, starting at the least significant bit. Alright, so here we've seen how we can split this binary number into groups of 4. Let's pad on the left with as many additional zeros as is necessary so as to create a group of 4 binary numbers, or bits. What we're then going to do is replace each group of 4 bits with a corresponding hexadecimal number. Alright, starting on the right, 1010. Well, that's represented by A. Next, going to the left, we see 1110. That is E. So we will replace that set of 4 bits by the 1 hexadecimal digit E. Next, we see 0010, and that's 2. So we'll replace that with 2. Next, we see 1101. Looking on the right-hand side, we see that that is represented or equivalent to D. Similarly, 1000 is 8. So we will represent that set of 4 bits by the hexadecimal digit 8. 0110 is 6. 1100 is C. 0101 is 5. And 0001 is 1. All right, so that binary number we had written down can be more compactly written as the hexadecimal number 15C68D2EA. We can also easily convert a hexadecimal number back into a binary number. To convert a hexadecimal number into binary, all we do is replace each of the hexadecimal digits with its corresponding 4 bits. So, for example, 8 is 1000, B is 1011, 7 is 0111, 0 is just 4 zeros, 3 is 0011, A is 1010, F is 1111 or 4 ones, and again F is 4 ones, and so therefore the hexadecimal number FFA307B8 represents the binary number that we see here. I'm not going to try to read this out. So in this course, you will not be required to add 2 arbitrary hexadecimal numbers. You should, however, understand the relative order. So for example, given this hexadecimal number, the number that comes right before it has a 4 in the least significant location, and the number that comes after has a 6 in the least significant location. Given this hexadecimal number, the number that comes immediately before it has an E in the least significant location. The number that comes immediately after it, well, F plus 1 is 10, and so we write down the 0, carry the 1. 1 plus F is again 10, so we write down the 0 and carry the 1. A plus 1 is B, and so we write down the B. Similarly, given this hexadecimal number, the number that appears right before it is 0F, and the number that appears immediately after it is 1, 1 in the least significant locations. Now, you could go crazy about this. You could create multiplication tables and addition tables for both binary and hex. You could memorize these multiplication tables. You could memorize these addition tables. You could define binary and hexadecimal multiplication and division. You could define floating point numbers in both binary and hex. You could calculate the square root of a number in binary and hex. Everything you can do with decimal numbers, you can do in binary or hexadecimal. However, all of that is beyond the scope of this course. You don't need that for this course. What you need is what we've covered here. You need to be able to convert between binary and decimal so that you understand the magnitude of a binary number. You have to be able to add 2 binary numbers. You have to be able to convert between binary and hexadecimal numbers, and that's simply to get a more compact representation of a binary number. You must understand the relative order of both binary and hexadecimal numbers. That's about it. Consequently, following this topic, you now understand that computers are going to be using binary numbers and that the binary digits 0 and 1 are called bits. Binary numbers themselves will be prefixed by a 0b. You see that binary addition mirrors decimal addition. You also know that there are hexadecimal digits that include the digits 0 through 9, but also have the additional hexadecimal digits A through F. You understand that binary numbers are verbose and hexadecimal numbers are a more compact representation of binary numbers. Hexadecimal numbers are prefixed by a 0x. You know how to quickly translate between binary and hexadecimal numbers, and you at this point do not care what the decimal value of a hexadecimal number is. If you did, just convert it into binary and then convert into decimal.